Um, Tonight's talk is Transparent and Accessible Vaccine Appointment and Delivery System by Steve Sutton and Doug Bodner, and Dave Eldridge, who I think was part of the work, is on site. I don't think he's presenting, but he's there with them. Just a little bit of background on this group of guys. Steve Sutton retired in 2011 from directing the systems engineering education programs at the University of Maryland, which he did until 2014, and now provides pro bono systems engineering services for non-engineering problems. He holds degrees from Rensselaer Polytechnic Institute and George Washington University. He's also a registered PE and an Incose ESEP. He's also our liaison to ABET and co-chair of the CIPR working group. Doug Bodner is a principal research engineer at the Georgia Institute of Technology, where he conducts research on systems engineering methods and analysis as applied to industrial and systems engineering and the Professional Masters in Applied System Engineering program. He's a member of ASEE, IEE, IISC, Incose, and Informs, and he is also a registered professional engineer in Georgia. Dave retired in 2020. He was adjunct professor of systems engineering at the University of Maryland from 2020 to 2021. For Incose, he served on the board of the Chesapeake chapter as faculty advisor to the University of Maryland Student Division and as a certification application reviewer. He holds degrees from the General Motors Institute, now known as Kettering University, Purdue, and Michigan State. He was a registered PE in Michigan and is an Incose ESEP. So with that introduction, I'll turn the podium over to our speakers.
Okay, well, my colleagues and I are delighted to be here tonight to reprise a presentation that we gave at the International Symposium in Detroit last year. And it's based on work we have done under the auspices of the Critical Infrastructure Protection and Recovery Working Group. And we're going to go through a number of things, but there's kind of some introductory things we want to say before we get to what we're actually going to talk about. And I want to remind everybody tonight that today is the anniversary of the Battle of Lexington and Concord, an auspicious battle in the history of the United States. It involved Paul Revere's ride, as well as the rides of other patriots trying to warn the coming of the British. And then you can see that the battle began early in the morning on the 19th in Lexington, and then moved to Concord, where the Concord Bridge. And after that, the British left and were forced to flee. But one of the things that today it would be if they hadn't changed it to a Monday holiday, is Patriots' Day in Massachusetts. And it's also the date of the Boston Marathon, and both events now are commemorated, and the marathon is run on the third Monday in April. So that gives me pleasure to provide that little bit of a history for you. And as I said, we've done this work under the auspices of the Critical Infrastructure and Protection Working Group. And I think I made a brief overview about the working group and its activities. And besides the project we're going to talk about tonight, we have some ongoing activities now. Right now, the Resilient Hospital Reference Model, which John Yu has, who comes from the Cleveland chapter, and is also involved with the Power and Energy Working Group and a couple of other working groups. But he's been leading this activity up with members. There are some members on his team from the Chesapeake chapter, as well as there are organizations outside of the Chesapeake chapter who are that involved with medical and hospital operations. We've also been involved with the Idaho National Laboratories. The three gentlemen, Tony, Dan, and Ryan, that are listed there, have been working on this project. Dan comes from he's our chairman of our working group, and he comes from the Naval Postgraduate School, and Ryan Ruska comes from the Idaho National Laboratories. In fact, there's a presentation from one of his colleagues from the Idaho National Laboratories tomorrow at 3 o'clock. And if anybody's interested, I can send the information to you. And then we are involved with this joint effort of a number of societies on cybersecurity of industrial control systems. And I don't have the date, but some of you may know Joe Weiss, who's from ISA, in the International Society of Automation, and he's giving a presentation on the security threat to electric vehicles. I think it's next week, and if people want to contact me, I can provide the information on that as well. And my contact information is on at the end of the presentation, and you can find me on the in the Incose directory as well. The 3 team members, Mike has given you the overview of us. Dave and I been with the Chesapeake chapter for many years. Dave is treasurer. I was about 20 years ago. I was the president, and Doug works with the Atlanta chapter, and he's a strong researcher at Georgia Tech. Well, one of the things we want to do, and every time we talk about this, is we want to thank the SALT Systems who give us access to a number of licenses of their Cameo Enterprise Architecture MBSE tool. And this has been very helpful to us on not only this particular project, but on the other 2 projects, particularly the Resilient Hospital Systems and the DHS project as well. And it's very, very worthwhile to have this whole system with their generosity for this. And one of the things, if you're not aware, is that in the near future, and I'm thinking in the next maybe 2 years, there will be a SE tool laboratory in which members can have access to tools such as this, as long as the tools are being used for Incose purposes. Now, here's our agenda. Why do we want to talk about an accessible and equitable vaccine delivery system? That's what the motivation we'll talk about. And once we understand the motivation, there are some operational needs that we're going to articulate, along with a set of measures of effectiveness. And then we're going to describe our implementation independent system design, which is based on the operational needs and influenced by the motivation. And we're expressing that with SysML artifacts, and that's where the use of the Cameo Enterprise Architecture tool comes in. The simulation, which Doug Bodner is going to explain to you, it doesn't use the Enterprise Architecture tool, but he'll tell you what tool it is using. And then when he'll also provide a little demonstration of the simulation that he's put together as so far. And then we're going to talk a little bit about, what can be done moving forward. Motivation. 3 years ago, it seems long time now that we were in this worldwide threat and a worldwide response where we all locked ourselves down. And I think I can tell by looking in the auditorium there tonight that we're still having impact on us as far as social activities. And we're more attuned to doing it like I am right now on Zoom instead of meeting face to face. But those lockdowns and the whole situation really was fearful for everyone. But the hope came with vaccines, a miracle in many respects because of the time it took, the minimal time it took to get the vaccines in place, tested, and out the door and ready for people. And we all, especially myself and my wife and family, were anxious because we are of an age that we were in the first set of people that were allowed to get the vaccine. And the question was, why is there so much anxiety? And I wanted to tell you that back in January 2021, when vaccines became available and were handed out across the United States to the various states, you could make an appointment. And since many of you live in Maryland, like I do, we're in Anne Arundel County, and Anne Arundel County had an approach. I think there was a website. You fill out the information, and then somebody was supposed to call you or email you about setting up an appointment. Except that didn't occur for us until I wrote a letter to the county executive staff, and I said, why aren't I getting appointments? Well, some of my friends are getting appointments. And we're all in the same age category. And they said, well, we lost some of the database because it was corrupted. And so we had to reapply, and we still weren't getting a request to get an appointment. And so we went outside. The state had a site, and it served a number of counties, and we were able to make appointments at the Prince George's County until they were canceled because the county executive there said their residents were not getting opportunity to get appointments. And so we tried some other means, and it turned out that some of the links we were given were not meant for us, but for first responders. So it was a very fretful time. And what had finally happened was I got a call from the county executive office one late January Saturday, and said, if you can get up to Glen Burnie, if people know where that is, there's a clinic there, and we have to give out the vaccines tonight because it's going to snow tomorrow. And so we had to get online and register again, and then drive up to Glen Burnie, where we finally got a shot. And that was a great deal of relief. And then everything else seemed to work effectively from there, because 3 weeks later, we were able to get our next shot. So we had the first 2 shots of the Pfizer vaccine. So it seemed to be like, who do you know? And if you can game the system, it was available. You could do it, maybe. But how should such a delivery system actually work so that anyone, anywhere, could make an appointment and get the vaccine and not have to worry about going through all these machinations and different places to look for? Even if you went to a pharmacy where it had limited access to vaccine, you couldn't get an appointment because they didn't have enough vaccine access for them to make appointments. And we also thought that if we could answer that question, maybe this is an application for systems thinking and systems engineering, and maybe we could learn a little bit more about using model-based artifacts to express ourselves in terms of the definition of this system we have in mind. And that system we hope would have these characteristics. We want it available to all who qualify, no discrimination. That's the equitable part. A single point of entry so that you don't have to go to multiple places, but there's different ways to get to that single point. And then the system should have the ability to validate eligibility, because at the time when we were conceiving of this, there were different phases, and you had to be a certain age category or have certain physical or medical problems that that would make you eligible for an early available dose of vaccine. You'd also want to give the users all appointments and choices of vaccine that would be available, so they can have that freedom to make that choice. Also, we want to avoid gaming the system and making multiple bookings, which gives others an unfair advantage. And we also want to ensure the integrity of the data that is presented to the users, held by the users, and transmitted outside the system, that it won't be tampered with. And we want the system to operate 24/7 for as long as it's needed. Now, the MOEs we developed, one is system capacity. That is, that it would support the system, supports the demand that is needed. The second one of the number of successful vaccines versus the number of appointments made would show that the demand is being met, and the time between scheduling and receiving your first dose of a 2-dose regimen or getting a booster is a measure of the availability of appointments and the availability of vaccines. So the shorter the time period, the better the performance. Variation in time to schedule or receive a second dose, depending on the vaccine, would show that the system is ensuring that the appointments conform to the medical requirements that are set for the giving the vaccine. Now, the design and implementation independent system definition. So we're not saying how this should be designed, but what should be the characteristics or actions of the system. And so we're using SysML artifacts to do that. Excuse me a second. You know, it's ironic today that I'm giving this presentation and I tested positive this week for COVID. And so my voice is a little scratchy here. Fortunately, that's basically the only problem I'm having. Okay, so here we use a definition diagram for a context diagram. And then we're using use cases. With those use cases, there are narratives that explain what's happening, the actions and assumptions associated with each use case, as well as also some stated requirements. And then the activity diagrams are based on these narratives for each use case and the actors that are associated with the use case. And then because there's requirements listed in here, we're able to create a requirements diagram. And so what I want to do today is give you a little taste of each one of these. First, I'll talk about the context diagram. And if you note, if you can see here, that it looks like sort of an IDEF0 diagram, where the system here, and this is a system that delivers vaccine in a United States state. And so the constraints are up here, inputs and outputs, and down here are the mechanisms. So in hopefully more readable form, here are the controls that we surmised for this. Remember CDC priority groupings, phase 1, 2, and 3, depending on your age and your medical condition. The system would also be limited and constrained by whatever medical standards are needed for operation of the system and delivery of vaccines. How much vaccine is actually allocated and given to the state. And we're making the assumption, at least initially, that the U.S. government, which provided the vaccine, through the Department of Health and Human Services, will fulfill all orders for vaccines. There's what's the guidance for administering the vaccine, and what financial resources that there are that constrain, you know, how the system can actually operate and with what resources. If we go to the next phase of the diagram, here's the block for the representing the activities of the system, and then inputs are the appointment requirements, the residents themselves that are partially or unvaccinated, and then the ordered doses that come in from the U.S. government, and then the outputs are orders data and records, communications, all communications to the media. And then we go to the bottom here, are all the mechanisms we defined, vaccine providers, various transport services to get vaccine around within the system, the two providers, the personnel that are required, supplies, and then communication resources. So all these things we defined. And then next thing is the use cases. We defined 7 use cases: registering for a vaccine, scheduling and keeping appointments, and getting the vaccine, providing status on your vaccine status that is available to the resident, ordering vaccine doses from the government and getting them to the provider, eligibility criteria, which is provided by the U.S. government, and then to be able to distribute vaccines. And the last thing is, communicating with the general community through media. That's part of a function of the system. Now, each one of these, as I mentioned earlier, has a use case narrative, or I'm labeling it as a type of specification. So you can see that has all the necessary basic information, a set of assumptions about that use case, who are the actors, what are the preconditions that have to be in place, what triggers the start, what is the main success scenario, what are the post conditions, the state afterwards, and then any exception cases, and that which can lead to additional narratives, which we did not have the opportunity to do. And then the last thing is the various requirements, functional, performance, and non-functional requirements. And as an example, this is the narrative for registering for a vaccine. And so the resident registers with a vaccine provider and obtains an appointment. So the assumptions are listed here, and some of them are: the resident has the knowledge of how to access the system, for instance, and he or she has access to some kind of device, or if not as smart, it's at least a simple phone to be able to get to a point, that single point of entry into the system to make an appointment. We are making the assumption the resident resides in the state and meets the criteria for receiving the vaccine. So the age, health condition, occupation, and location. And there are a number of other assumptions here that we postulated. The actors in this case is the resident, and the preconditions are that there is eligibility criteria established. There's a process to register for a vaccine, and the process and mechanism advertised is available to the residents so they know how to do it. Then the various triggers are, deciding to get the vaccine, but the resident decides to do that, and the resident can access the system through the devices that it's available to them. And then we have the success scenario, which I'll show in a different form when I show you the activity diagram. There are the post conditions that the resident has registered for the vaccine, and the resident can then get appointment opportunities from the system. And then we have some functional requirements that we postulated, even though we have left a number of TBDs. And then there's the exceptions. What if the resident isn't eligible? How does the system respond? What if there's walk-up registration, which is not part of the main scenario? How do we make that part of the system operations eventually? And the reason they're in red here is we have not addressed those at this time. Now, this isn't intended that you see everything here, but it's an interesting matrix swim lanes that that is available with the tool. And so the actors are across the top, and I'll show you that more specifically in a second. And each we put each use case along the side. So each swim lane in this direction is a use case. Each swim lane in this direction is for the actions of a particular actor. And since there were 7 use cases, there's 7 swim lanes horizontal. If we look at registering for a vaccine, you see that here the resident asks to register for the vaccine. There's a request for the information, both personal identifiable information and non-such information, which is then provided by the resident. Information is verified. There's eligibility criteria, which is available to compare against. And then if everything is good, then the resident is registered. And once the resident is registered, then he or she can go ahead and schedule the appointment. So you can, here's the system, here are the actors here, the resident, the system, and the vaccine provider. And so the system will offer the resident opportunities. They can make a selection. The appointments can be confirmed, and the user can put that in his date book. You can get reminder requests, or the system can remind them if they want. The resident will go to the appointment, everything is re-verified, get the vaccine, and then you can then schedule your next dose, and eventually you get to be fully vaccinated. Or if you're getting just a booster, you just get this whole process would just go through once. So that's the examples of the activity diagrams. Under system requirements, as I stated, the use case narratives, we created a number of requirements associated with each use case. So there was some repetition in that, and we called that out, and we were able to create a use case diagram, which kind of looks like this. And you see this 7 green sets of requirements here, which represented up here. And then there's requirements that are non-functional, and others that are for data protection, and we color-coded them as yellow, I guess, or salmon over here. And I'm going to go through a couple of examples. This is where the resident registration for a vaccine set of requirements. System shall register residents for the vaccine. And then there are some performance requirements here in terms of how fast that the system is constrained to do it. And sometimes if you're dealing with a smart device, that response time is going to be faster than if you're dealing with the system has to deal with someone who's on just a normal telephone or cell phone. And then there's the appointment scheduling, and there are performance requirements and additional functional requirements set for that as well. So you get the notion of how we put that together. Now, I'd like to turn over the presentation time to my colleague, Doug. And Doug, you tell me when to flip the slides, and I'll do that. And then when you get to the simulation, I have it ready to run, and I'll unshare and reshare that.
Okay, sounds good, Steve. Thanks. So really the motivation of the simulation is to be able to test this design and see how it performs under different scenarios. So a scenario is just a collection of perhaps input data. What's the demand? Are there production and supply chain problems? Those types of things that we can really stress test this design on. So some of the questions we might look at are, does the system have enough capacity to meet that demand? Are there certain barriers to vaccination? Steve mentioned this notion that it should be available to everyone without discrimination, but perhaps just because of where the locations are, for instance, that there is some amount of built-in discrimination occurring. And then Steve went through a number of requirements, and we can test out using simulation whether the system is meeting those various requirements and performance measures. So we can see what's the percentage of patients that are being accommodated with appointments. That gets back to the capacity, right? Is the appointment capacity really a bottleneck? And is it delaying the time between scheduling an appointment? So understanding the flow relationship of the patients as they go through the system and touch these various places to get their first shot and then their boosters. Is that working all right? Of course, there's a time constraint between getting shots that should be met, and is there enough capacity in the various vaccine delivery places, providers and such, that time constraint is being met. A couple of technical constraints is that many of the vaccines require cold storage, which is an interesting supply chain problem. So many places had to develop or purchase cold storage, and is that cold storage being met throughout the supply chain, not just in the storage at the vaccine sites, but also in the delivery. So, and of course, there's some amount of spoilage. For instance, one of the technical details that we have not modeled this, but the vaccines are delivered in, essentially, you might think of them as cases where there's X number of vaccines. And if you open a case to take out one or two vaccines, then there's a certain amount of spoilage time that comes into play for the remaining ones. So if you open a case, you need to use all the vaccine doses in that case within some time allotment. Otherwise, you get faced with spoilage, and being able to measure that would be important. So next slide, Steve. So we're just kind of doing the what you might think the physical performance of the system. Steve mentioned a number of IT requirements for the scheduling system, such as being secure. So we're not considering that in this version of the simulation. That could, of course, be built in at some later date. So essentially, scheduling and delivery and supply chain issues. We used a particular type of simulation platform. For those of you familiar with simulation, there are several variants, discrete event and agent-based are two prominent types of simulation. And we selected the AnyLogic platform because it has a pretty powerful free version that is available for educational purposes, which is what we're using it for. It supports both of these simulation paradigms. So both the discrete event, which is good for modeling the flow of patients through a system, for instance, and an agent-based, which can give us a lot of detail into how individual elements within the system behave. And it's one of the things you can think about there is it's quite analogous to the activity diagrams that Steve was talking about. It's basically a Java platform, and if the simulation model doesn't provide all the functionality to model things that you want, you can extend that by writing code in Java. So next slide. So the simulation is a small scale prototype, and we're really just trying to provide an example of how simulation can be used with a system design that is developed in SysML. And of course, the simulation model should be consistent with the model diagrams that Steve developed. One of the questions we got when we presented this before is, well, can't you just generate simulation model from the SysML model? And some amount of research has looked into that. It's very complicated problem, and it's been demonstrated for some fairly simple systems, but scaling it up to a system like this vaccine delivery system would involve a lot of work. So that's really an area of future research. And then what we really wanted was a data-driven simulation model where we could plug in different scenarios, which are essentially the input data, like I mentioned before, and then perform some analysis and performance measuring of how the system design works based on that data. So the data could be things like demand, it could be the size of the system, the number of vaccine delivery sites, where they're located, how many doses we have, what's the system capacity, those types of things. So next slide, Steve. A number of important simulation components. Of course, we have patients that flow through the system. They register for appointments. They go to the appointment site and get their vaccines. Then they come back after every so often and make a new appointment to get the next shot. And they go through that process. Of course, not all patients show up for their appointment. So there's some amount of leakage in the system in terms of the patients that are being served. Appointment calendars. So there's an appointment calendar construct. So a patient can select which appointment they want. Perhaps they want the first available, or perhaps they want an appointment at a specific time. And also the appointment calendars provide locations. There are some vaccine centers. So there are several different types of vaccine centers in the model, hospitals, pharmacies, and such. The vaccine providers, so these are the healthcare providers. So the people that own the pharmacies, the pharmacy chain, or the hospital system would be vaccine providers. And then the way the supply chain works is the state will send vaccines to the vaccine providers, and then they allocate them to the vaccine centers based on essentially an inventory model that I'll talk about a little bit more in detail. The vaccine doses themselves. So, a vaccine dose has to be available at the vaccine site in order for a patient to receive the vaccine. So what are the number of doses that are available? And can we figure out, well, we just don't have enough doses available to support all the appointments that have been made. And what happens in that case? How can we measure the performance? And of course, as Steve mentioned, there's a good bit of eligibility criteria in the beginning of the pandemic and vaccine delivery process. So how do those impact people in terms of who can get a vaccine, what percentage of the population, and then what happens if somebody tries to schedule an appointment and they actually don't meet the criteria? So they can come back at some future point when they do, or perhaps they don't come back at all. So next slide, Steve. So this is the initial scenario that we developed with 3 vaccine providers, just a small scale prototype, as I mentioned, with 8 vaccine sites. And I think we've actually expanded it since this slide. So I think we do the first 3 shots now. So the first and second shot and then the booster for the Pfizer vaccine at least. The patient model has been expanded to where we essentially have a patient arrival process to the appointment registration process. And so however long we want to run the simulation would be the number of patients. As I mentioned earlier, we have an inventory model where it's essentially an order up to model. So when one of the vaccine sites starts to get down to the reorder point for the number of doses, then they put in an order to the provider for a set of doses to get us up to what we would like to have as our max inventory. And hopefully the provider, if they have enough doses, can provide that. So there's the possibility of a stock out. Any one of the sites who run out of doses and not receive doses in time to have patients that show up for appointments and are not able to get shots. And then there's the patient appointment scheduling model. So this is essentially the patient's registered, they select from the available appointments, and then they show up to their appointments at the time, or perhaps with a small probability they don't show up. So next slide, Steve. This is just a performance dashboard, and we can see up at the top, and I kind of use Georgia as the state, and we're assuming that Georgia gets a lot of doses from the federal government at time 0, and then they gradually decline. And there's the 3 vaccine types that are represented in the different colors, the yellow, blue, and green. And this is just the inventory level of each over time. And this is once again just a scenario, not really based on any real data, but just to illustrate how a model like this might operate. And then the state provides doses to the various providers, and you can see the inventory diminishes over time. Sometimes it goes down to near 0. Sometimes it reorders and receives the dose before it gets to 0. And then the inventory jumps up after the delivery of doses is received and starts declining again. So this is a pretty typical inventory replenishment system. And then the various sites operate pretty similarly. You can see the scale is a much quicker, right? Because they don't have as many doses at each site. So the demand kind of takes the available doses and uses them much more quickly. So the reorder cycle is much more frequent at the sites that are delivering the doses to the patients. And then down at the bottom, we have some performance measures. How many shots of each type are we giving out? What were the number of shots that we were short? How many people didn't get a vaccine because we did not have doses when they showed up? And then we can see on a daily basis the number of shots that are given out. And, we can see, if you look at the diagram, you can see kind of a weekly cycle. So we're kind of assuming that some of these sites are not open on Saturday and Sunday. And then there's a graph that shows the number of shots that were short as a function of time. So, and this is an animated display that we'll show you during the demo. So, Steve, let's roll a demo.
Okay, let me, I have to stop sharing here. And then I have to share. I think it's this one. And load it.
Okay, so there should be audio with the demo, Steve, and I'm not hearing anything.
Steve, what we found was that when you share, when you hit the share button at the top, you'll see a slider that says advanced, beginner, and advanced. If you click advanced, it should give you an option to share video. And then I think the audio and video will come through.
Is the audio not going through?
No.
Oh, okay. What was your suggestion?
So if you open up that share screen again, and then at the top, there's like a slider, then it says beginner, advanced, I think.
Let me stop sharing again. Oh, right. Advanced.
Yeah, and then over to the right, it'll say video. And if you click on that one, then it asks you the location of the video.
Doesn't ask for a location.
Okay, if not, let me see if I can do it real quick because I had it set up. Let me see. There we go. Share. Hang on. It's video. There you go. When you hit share, it does it. Okay.
This is a demonstration of the prototype simulation model for vaccine last mile delivery. First, we will go through the model structure, and then we'll show an animation. So essentially, this models how COVID vaccines are going to be delivered from the state government to a particular resident. This is an agent-based model. You can see on the left hand here, there are some agents defined for the resident, the state government, the vaccination site, and the vaccine provider. To the extent possible, we are making this a data-driven model, and that really applies to the state, the vaccination sites, and the vaccine providers. So the data that populates their attributes in the agent model is represented in the database, and that's read into the agents when the simulation starts. The residents, on the other hand, are generated randomly. So each resident has a particular risk level, a particular age, a race and ethnicity, and those will drive how the residents interact with the overall system. And we can see down here toward the bottom, there's a process model that defines the resident life cycle through the vaccine process in terms of making appointments and such. So the new resident accesses the system checks eligibility based on requirements that are defined in the model. And if the resident is not eligible, there's a delay and the resident has to wait to become eligible. And the eligibility can change over time. So if that change does occur and the resident becomes eligible, they can log into the system and try to register again. If the resident, on the other hand, is eligible, the resident can register in the system, make an initial appointment. And we build in delays to this process to represent the various touch points that the resident has with the system. And these touch points are consistent with the SysML model that's been defined. So there's a registration process and appointment process outlined in the SysML models. And that is basically what the resident goes through each time they make an appointment. And we can see that depending on the vaccine chosen by the resident, whether it's one of the two-shot Pfizer or Moderna vaccines, they may need more than one shot initially, or they can just get by with one shot if they choose the Johnson & Johnson. And then the resident can make the additional appointment for the second shot, and afterwards they can make appointments, and there are delays between those appointments represented for the different boosters that the resident may elect to receive. So that's the basic life cycle that the resident goes through. Let's talk a little bit about the delivery system itself, and I'll switch to the animation interface here. So this shows the simulation as it executes over time. And there's an inventory-based model for each of the vaccination sites. And this is an order up to system. So demand is driven by patient appointments and those vaccination sites. And eventually those doses run out and a reorder has to be put in. So each of these sites we can see is basically tracking how much of doses of each vaccine they have. And when they run down to the order point or the reorder point, they will order from a provider and the provider will provide a shipment. And similarly, if the providers run down to their reorder point, they will put in a reorder to the state for additional vaccines. And we can also see down at the bottom that the number of shots administered per day and the number of shots that might be short per day are also being tracked by the simulation, as well as the total number of shots and such over time. So this is a very simple simulation model. We assume that patients or residents do attend their appointments, although we could certainly add in missed appointments. And there are many complications that can be added to the model, and we can test different scenarios. So those are some of the future things that we would consider doing with the model. And we will be glad to take any questions at the end of the presentation. Thank you.
You'll unshare, and then I'll put up the rest of the slides.
Okay, hang on.
Mhm. Okay. Back to where- go. Okay. Just a second here. There. Okay. Doug, you wanted to, maybe you covered this already.
Yeah, I'll say a few words on this. So a longer term goal would be to take the animation database that we have and add to it what I'm calling a controls dashboard. So the different scenarios that we mentioned, we would have control sliders, radio buttons, and things like that to represent what's the demand level from the residents. Can we change that during the simulation run and spike it to see what happens? Can we add in supply chain disruptions? So maybe there is, a shortage of drivers, so we cannot get the doses that are available out to the sites. So things like that we can use to test out different scenarios by the person who's running the model. So it doesn't have to be programmed; it's just part of the dashboard that the user can play with. And so add some additional visualizations of the system performance. So we didn't really show the number of people who were tried to register for the system and they were rejected because they were not eligible. We didn't show any distinguishing things about who's being rejected or who may not be able to get appointments because they aren't near a vaccine site. So getting back to this notion of no discrimination. And then what we have so far is just a visual representation without any real statistical analysis. So the simulator has quite a number of statistical output functions where we can do some hypothesis testing and test out, is this feature for the design better than having, that other set of features. So we can use a lot of statistical analysis as well. Next slide.
Thank you, Doug. Yeah, there's a couple takeaways that we wrote down, sort of lessons learned. or observations. This may seem obvious, but you can't easily define a system without collaboration. It takes a team. And we were, a few number of guys trying to do this on our off off hours, in a sense, trying to do this, and there was a lot of thought process that goes beyond into this, and I can't tell you how many times we revised the narratives and then the use case diagram and then the activity diagram to support that. Was an iterative process, and it drove me a little crazy after a while, because every time we did it, it seemed like we either undid something or redid something, and but it's a quite an intensive process, and it does take a team of people to keep everybody sane and to get a result that's useful. And we also found, at least with Cameo, Doug was much more capable with any logic than either Dave or I were with Cameo. But to use a tool like Cameo effectively, you really need to have some basic understanding of how best to use the tool. We did have some tool experts who gave us some advice about how to simplify our diagrams, what to put in, what not to put in, and which was helpful. But it was you really need, I think anybody who uses this tool really needs some basic training, rather than just starting in and using it. The tool is based on Magic Draw, and was expanded based up from that, and so I had some familiarity with Magic Draw, so that made it a little easier for me to use the tool, but I couldn't necessarily use it effectively, and but that's another lesson learned. And how best to use the tool given the way, at least I use with my systems thinking paradigm, and be able to adjust without letting the tool override my thinking process. So that's another aspect of using a tool, and again, using a language like SysML as the basis for developing these definition artifacts. Moving forward, we are still looking for additional volunteers who would like to take this design process further. We've been trying to get local health departments to take an interest in this, to see whether our ideas about how this should work matches their own thought processes, where they see the tools that were used during COVID, where this could provide some additional value. Could this be a reference model for a system? Because as I think we all understand, or at least I do, that there could be another pandemic with another type of virus, or that could cause the same problems. It would be nice to have systems in place, not only for how to deliver the vaccine to the users, but also the whole process of being prepared for such an event again in the future. We have not been successful in talking to local health departments. I've tried 2 different methods over here in Anne Arundel County, and I have not been successful with that. Other thoughts, we made overtures to the healthcare working group, but nobody ever responded to us, unfortunately. If there's anyone who's involved with a student division or a graduate program or a senior capstone program course, looking for a project, this might be the kind of thing to do that allows you to exercise system engineering design principles and on something that has some potentially benefit to mankind. It could be part of a course on a system engineering course on healthcare applications, or we also thought maybe there's some using it as an example in a short course on applying systems thinking. And any other thoughts on, how to make use of this work? We'd certainly appreciate hearing from anybody. And that's our presentation. We thank everybody for listening tonight. This is our contact information. If you're interested in tomorrow's presentation at the super working group, I can provide that. And also I can provide that information on the presentation that Joe Weiss is going to give on his talk about the vulnerabilities of electric vehicles. Thank you very much. And I will unshare.
Okay, thanks, guys. Any questions?
Yes, this is Steve Beamer. I'm here at APL. And I do have a question, Steve, for the use cases that you developed. You partially answered the question in your moving forward slide. I was going to ask you whether you were able to contact anyone from the health departments, and I recognize the challenge in doing that. Were you able to acquire any other sources of information in order to assist in developing use cases, or were they primarily sort of an ideal set of use cases?
Well, I think there are, at least what we wrote down was the ideal, at least in our mind. So I would have liked to have had, a practitioner in the health department talk about some of their problems and, how we can or can't help with that. But we didn't have that opportunity, and not at this time anyway.
I'm hoping that some data will become available, in some of the analysis of our COVID response, and that might help. But I haven't seen any, and I've been working in some of the healthcare field systems engineering work, so I'm not sure why the delay, quite honestly, in the after action reports, et cetera. But maybe they'll come out. I'm hoping. And actually, I have a corollary question, Doug, for you. Along the same lines, in gathering data, were there any public sources available in either Georgia or any state in the union in terms of things like wait times and facilitations or percentage of shots and doses? I'm not aware of any, but I was wondering if you had gathered any.
There's nothing publicly available that I know of. So we had a related project a couple of years ago where we were looking at essentially capacity. And this was a funded project. And we had partnered with some local outreach agencies who were, giving shots to essentially people in the area that they served. So they had some of that data, but it was kind of really spotty. Only, and they didn't have wait time data. They had, essentially number of patients that showed up, and presumably they also had the appointment date as well. So it's not clear to me that a lot of that data was captured in terms of anything other than the number of patients who showed up and maybe who was not able to be served. So things like that. Part of that is manpower, of course. They're busy actually delivering the doses, right? Having people, especially the ones we worked with, which are nonprofits, having people to collect those statistics, I think, is problematic.
I definitely feel your pain, having gone through a couple of programs. Finding data, especially publicly available data, is just a humongous challenge. So yeah, kudos for what you were able to do without publicly available data. And it's going to continue to be a challenge, I'm sure.
Yeah, this is Mike Ali. One question on the simulation. Did you play around or how did you do the scheduling? So if somebody, if a patient requests an appointment at the provider, and they don't have enough inventory or too many people applying, you know they're going to run out. Did you have anything that would push out the date, or how did you set the date when someone asked for an appointment at the provider?
Is we didn't build in a lot of sophisticated logic like that. So there is a set of appointments available and the patient signs up for one.
Okay.
And, I think what we, ought to do is as the next step to some of the things that you're saying is do a better job matching the available doses to the appointments. So, actually canceling some of the available appointments because we don't have enough doses, it would be a valid thing that should be implemented in the system.
And then did you ever break the scenario? I mean, you break the simulation. Did you try running like 10,000 people or 100,000 just to see what would happen?
Well, we did increase the arrival rates, which is the same thing that
Yeah.
you're talking.
Mm-hmm.
So you can see that, you run the model on the dashboard, you start running out of doses quite a bit more quickly. And then, you have more people that are not able to get them. So there's the number of doses is short, kind of skyrockets. But you can play around with that type of analysis fairly straightforwardly by just changing the input numbers in the simulation.
Yeah.
Hey guys, I had a comment. You mentioned Doug there in slide 32. It was going to be a question, but you sort of covered it in slide 32 about logistical complications that for further considerations. I actually experienced a logistical complication. I was not in the first priority bunch to get the vaccines. So I was eager when I did eventually get an appointment. I was eager to get the vaccine applied, and then after that, there was a bit of relief. I was like, yes, I'm safe. I didn't. But then a day later, I got a call from the administrative facility, and they said that there were logistical problems with that batch they gave me, and there was a recall, so I had to come back and get re-administered. So I had to get rescheduled for all that and stuff. So I just want to make that comment. I don't know if your model as it is now would handle a use case or scenario like that, but I certainly experienced it.
Yeah. So doesn't right now, but that's a little bit similar to the trucker availability issue that I brought up. So we think that this batch of doses is going to be delivered, but because of the labor shortage, we don't have a trucker to drive that truck. So all of a sudden, a bunch of doses are not going to be delivered to the various provider sites.
And the conditions, these vaccines, some of them were very delicate. So they had to be handled, in very cold conditions. They had a shorter shelf life and all that. So it's not like, something like happened to it, like, fell off the truck type of thing. It's more like they had to plan for this particular type of administration of this.
Yeah, so you really have to match the demand, your predicted demand to what you're going to deliver, because in most inventory systems you have either a shortage or an overage, and the shortage cost is typically a lot bigger than the overage cost. And, the shortage cost of the vaccines is big. And the overage cost is typically just the cost it takes to store the inventory. But now you have spoilage, which starts making the overage cost quite a bit. So, so now you have to really balance your expected deliveries with the demand, because previously in a typical situation, who cares how much inventory? You care a little bit, but you don't. It's much better to have a inventory buffer, kind of a safety buffer for demand spikes. But here, having that may not make too much sense.
This is Dan O'Neill. I have 2 quick questions. First is, are you out of Atlanta?
Yes.
And then the second question, which will come back to the first question, are you familiar with the website vaccines.gov?
No.
CDC and Boston Children's, they created a tool to find what you were looking for. I'm a little bit disappointed that it's not publicly known when I got a lot of smart friends in the room. But vaccines.gov, and then CDC group down there called HPOP, Health Partner Operational Portal, HPOP, vaccines.gov. I think if you follow that up, there's folks down at CDC, in particular, Captain Bobby Rosolina. It's hard to say, but anyway, he was at Health and Human Services. It's now down at CDC. Vaccines.gov has
great.
what you're looking for. I love the fact that you are reaching out to state and local entities, because at least last time and probably going forward, state medical boards are kind of the linchpin to all of this. So, if we here in Maryland, if we can connect with the medical board here, or if in Atlanta, you did it down there in Georgia, here in Annapolis, or wherever we'd want to do, that would be, I think, the linchpin. And your model appears to be of the size that a state could get its head around. What are you trying to model? So, well done. Thank you.
Any other questions?
Oh, is this published somewhere that it can be read or given to others, or are we just special Incose folks?
Is it available publicly, the presentation?
Other than this presentation, you guys publish anything that's out there?
No, this was the only thing we, in a sense, published. It was presented at the symposium last year, and I think we gave it again last September just for the SIPR working group. But I guess that's another something we could do. But I think we should do more work before we try to make it a formal paper.
Yeah, I was just trying to have a way to show people. Unfortunately, we got this on video, so we can give them a taste of it. Thank you.
But Mike has both the presentation and the simulation description video, so that can be made available.
I mean, that's up to you. Do you want it to be made available if someone asks for?
Yeah, that's fine.
Okay.
Yeah, that's
It's
fine.
it's an Incose, in a sense, an Incose product, and I think we put it on Yammer in our Yammer group for SIPR.
Okay. Also, I assume Incose must have it somewhere. If you presented it last year, they must have it somewhere in their proceedings.
Yeah, that it's hard. It's hard to get access to those.
Okay, well, that's fine. If people need it, like I said, they can send me an email.
Check the SIPR Yammer group. That's open to anybody, and I think we put it there. If not, let me know.
Okay, anything else? If not, we can go to the, go ahead.
Sorry, I had a really quick question. I'm sorry if you covered this. Sean McGurvey from here in APL right now, but I wanted to find out, first of all, great presentation, and I love your modeling. It's awesome. I was curious if you had done maybe a sensitivity analysis for your simulation. and maybe had any conclusions on what technical measures had the biggest impact on the measures of effectiveness that you were tracking?
No, we haven't done that. We've just really done the basic scenario. So I think, at least one next step would be really tweaking the things like demand, the supply chain problems, those types of things that we talked about. And seeing how that affects the performance measures. So that's certainly an area of future work for us.
Okay, thank you.